Hey, welcome back. So today, we're jumping into something called molecular orbital theory. Now, this is one of those really powerful ideas in chemistry that we pull out when the simple models just don't cut it. And it helps us explain some seriously weird behavior, like why a substance we're all familiar with can do something that seems to defy all logic and actually stick to a magnet.
You know, all those tools we learn in chemistry, like drawing Lewis structures, they're fantastic. I mean, they get us incredibly far in figuring out how molecules are shaped and how they bond together. But every so often, nature throws a real curveball, a puzzle that our trusty everyday tools just can't seem to solve.
And this is one of the most famous curveballs out there. What you're looking at is liquid oxygen. It's been cooled down to a super chilly minus 183 degrees Celsius. And as it's poured between the poles of this really strong magnet, whoa, see that? It doesn't just flow through, it sticks. It's actually being held there, attracted by the magnetic field. The big question is, why on earth does that happen?
Okay, let's break this down. Our usual go-to model, the Lewis structure for an oxygen molecule, O2, shows a nice, neat double bond. But here's the key. In that drawing, every single electron is paired up with another one. Now, the rule in chemistry is that when all your electrons are paired, the substance should be diamagnetic. That means it should actually be slightly repelled by a magnet. But, as we just saw with our own eyes, reality is the exact opposite. Oxygen is paramagnetic. It's strongly attracted. So, our simple, reliable theory is completely wrong here.
And this is exactly why science is so cool. You know, when a theory doesn't match up with what we observe, it's not a failure. Not at all. It's an opportunity. It's the universe basically telling us, hey, you need a better model. You need to go a little deeper to really get what's going on here.
And that deeper model requires us to think about electrons and where they live in a molecule in a totally new way. We need to move beyond the idea of atomic orbitals and introduce a whole new concept.
And that brings us to molecular orbital theory. The core idea here is a real game changer. So instead of thinking about electrons belonging to their individual home atoms, MO theory says that when atoms come together to form a molecule, they create a brand new set of orbitals, molecular orbitals, that cover the entire molecule. The electrons aren't just stuck on one atom anymore. They're free to move about the whole thing.
This is just the perfect way to think about it. You know how an atom has its set of orbitals, the 1s, the 2s, the 2p, right? Well, a molecule has its own unique set of orbitals that belong to the whole molecule. It's really the same idea, just scaled up from an atom to a molecule.
So, how do we get these new molecular orbitals? Well, we use a method that sounds fancy, but the idea is simple. It's called the linear combination of atomic orbitals, or LCAO. Basically, we take the original atomic orbitals and we mathematically combine them. And here's the most important rule of all. The number of molecular orbitals you make is always the same as the number of atomic orbitals you started with. You put 2 in, you get 2 out. No orbitals are ever lost in the process.
Now here's where it gets really fascinating. When you combine those atomic orbitals, you don't just get more of the same. You actually create 2 fundamentally different types of molecular orbitals. One that helps hold the molecule together, and one that, well, does the opposite.
Let's make this real with the simplest molecule possible. Hydrogen, H2. We start with 2 hydrogen atoms. Each one brings its single 1s atomic orbital to the party. When they get close enough to form a molecule, those 2 atomic orbitals mix and combine.
And they create 2 new molecular orbitals. So take a look at this energy diagram. On the sides, you can see the energy of the original 1s atomic orbitals. But in the middle, you see the 2 new molecular orbitals they formed. One of them, called sigma 1s, has actually dropped to a lower, more stable energy. But the other one, sigma star 1s, has been pushed up to a higher, less stable energy.
That lower energy orbital is called a bonding orbital. This is the good stuff. It's the molecular glue. Putting electrons in here makes the molecule more stable because it concentrates the electrons right between the 2 nuclei, pulling them together like a chemical hug. The higher energy one is called an antibonding orbital. It's bad for bonding. It's destabilizing. And it actually has this dead zone, a node, right between the nuclei which actively pushes them apart. So to figure out if a molecule is actually going to be stable, we need to see if the glue is stronger than the push. And we do that by calculating something called bond order. The formula is super straightforward. It's just 1/2 of the number of electrons in those good bonding orbitals minus the number of electrons in the bad antibonding ones.
Let's try it for our hydrogen molecule. It has 2 electrons in total, and since nature always fills the lowest energy level first, both of those electrons will pile into that stable, low-energy bonding orbital. So, our calculation is 1/2 of 2 bonding electrons minus 0 antibonding electrons, which equals 1. A bond order of 1 means a stable single bond. Hey, it works! But now, let's try it for a molecule we know doesn't exist, like 2 helium atoms trying to bond, He2. Helium would have a total of 4 electrons, so the first 2 would fill up the bonding orbital, but then the next 2 are forced to go into that high-energy, destabilizing antibonding orbital. The math becomes 1/2 of 2 minus 2, which is 0. A bond order of 0 means no bond at all. The stabilizing and destabilizing effects completely cancel out, and that is exactly why helium is a noble gas that just hangs out as individual atoms.
Okay, we've got the tools, we understand bonding orbitals, antibonding orbitals, and how to calculate bond order. It is time to go back to that original mystery and see if this new theory can solve it.
So let's finally get to the bottom of this. Why in the world does liquid oxygen stick to a magnet when our simple model said it absolutely positively should not?
This is the molecular orbital diagram for O2. Now, I know, it looks a lot more complicated than the one for hydrogen. That's just because oxygen is using its s and p orbitals. But don't worry, the principles are exactly the same. We have a ladder of low-energy bonding orbitals and high-energy antibonding orbitals. Now, each oxygen atom brings 6 valence electrons to the table. 2 atoms means we have a total of 12 electrons that we need to place into this diagram, starting from the very bottom and working our way up.
And there's one last really crucial rule we have to remember, Hund's rule. You probably remember this from basic chemistry. It's the one that says when you have orbitals at the same energy level, electrons will fill them one at a time before they start pairing up. Think of it as the everyone gets their own seat on the bus before anyone has to double up rule. It applies to molecules too.
All right, this is it, the moment of truth. Let's start filling. We put 2 electrons in the sigma 2s, 2 in the sigma star 2s, 2 in the sigma 2p, 4 more fill up the pi 2p orbitals. Okay, that's 10 electrons so far. We have 2 left. They have to go into the next energy level, the pi star 2p orbitals. But wait, Hund's rule. Those 2 orbitals have the same energy, so the electrons don't pair up. One goes into the first pi star orbital, and the last one goes into the second pi star orbital, and there it is. Look at that.
Do you see it? Molecular orbital theory predicts that an oxygen molecule has 2 unpaired electrons, and unpaired electrons act like tiny little magnets. That is the very definition of being paramagnetic. The theory perfectly explains the observation that totally stumped our simpler model. The mystery is solved.
So let's just recap what we found. MO theory doesn't just solve the magnetic mystery, it gives us a much more complete and accurate picture of what bonding is really like. And what's so incredible is, if we now calculate the bond order for oxygen, we have 8 electrons in bonding orbitals and 4 in antibonding. 1/2 of 8 minus 4 is 2, a bond order of 2. It correctly predicts the double bond that our simple Lewis structure showed us all along. It keeps the part that was right, and it fixes the part that was wrong.
This is just such a beautiful example of how science works. You start with a simple observation that seems to break all the rules, and it forces you to develop a more powerful theory that opens up a whole new way of seeing the world. It really makes you wonder, what other chemical secrets are just waiting out there for this theory to unlock?